Okay, going to go through some examples from Worksheet 5, which is about units and dimensions, and we also cover proportion in there. So let's go straight in. I'm going to do something about question 2 because that covers a lot about proportion. And here I'm asking you to convert 0.01% into various different other ways of expressing that proportion. So one thing we need to remember is that 0.01% is 0.01 parts per 100, and we can write that like that. And actually, that's going to help us. A way that will help us with the later bits is to write this as 10 in the 10 to the power way. So 100 is 10 squared, 10 to the power 2. 0.01 is 10 to the minus 2. 0.01 is 100th, so 10 to the minus 2. Okay, so I asked you to convert this into parts per 1,000. So at the minute we've got parts per 100. So if we want to go to parts per 1,000, what we're doing is we're going to change this bit at the bottom, 10 squared, into 10 cubed. We want to go from parts per 100 to parts per 1,000. So what we do at the bottom here is we've multiplied that by 10. Now with a fraction, whatever you do to the bottom, you have to do to the top in order to keep it the same. So trivially, we could think of 3 over 6. If I multiply the bottom by 2, make it 12, I have to multiply the top by 2 to keep it equal. Same again, if we multiply the top by 2, we have to multiply the bottom by 2. So all these are equal. So whatever we do to the top, we have to do to the bottom in order to preserve the equal sign. So therefore, we need to multiply this by 10, which gives us 10 to the minus 1. So 0.01%, written like that. If we convert that into parts per 1,000, it's 10 to the minus 1 parts per 1,000. So another way of writing that would be 0.1 parts per 1,000. Remember, parts per 1,000 is like the percent sign except with 2 zeros down here. Okay, we'll just do one more from here. We'll going to parts per billion. So 10 to the minus 2 over 10 squared, 0.01%. How are we going to convert that to parts per billion? 10 to the 9 is billion. So going from here to here, we've multiplied by 10 to the 7. Therefore, we have to multiply the top by 10 to the 7. Minus 2 times 10 to the 7. 10 to the minus 2 times 10 to the 7 will be minus 2 plus 7, which gives us 10 to the 5. 10 to the 5 is the same as 100,000. So that's 100,000 parts per billion, and that's how we write parts per billion. So for parts per million, which is the other part of the question, that's 10 to the 6, and we'd write that ppm, and I'll let you work that one out by yourself. Okay, question 3 has got a lot of unit conversions in it, and what I'll do, I'll go through the very last one because that's the one that's a bit more complicated because you're having to convert 2 units. So I asked you to convert 20 milligrams per litre into kilograms per metre cubed. So volume in litres to volume in metres cubed, mass in milligrams to mass in kilograms. And I'll give you some conversion factors. 1 litre is 10 to the minus 3 meters cubed, and 1 milligram is 10 to the minus 6 kilograms. Okay, so we can give these, let's give these conversion factors units, so that sort of helps us on our way, and this would be a bit like as we did in the previous worksheet where we converted kilometers cubed into meters cubed. So this, what we're saying here is that there are 10 to the minus 3 meters cubed per litre, and in here we're saying there are 10 to the minus 6 kilograms per milligram. Okay, if you remember the technique that we started to use when we were going last time is that we want to be able to cancel out the units here in order to be able to get us to here. So here, if we just look at litres, we are going to want to convert we want to have the litres on the top, basically, so that our litres, we want this in the format of litres per metre cubed in order to help us get from cancel out this litre. So at the minute, we've got metres cubed per litre. So if we were to multiply this by 10 to the minus 3, then we'd have litres squared underneath, which doesn't help us. So we need to invert this so that it's litres per metres cubed. So take the reciprocal of it, invert it. So that then becomes 10 to the power 3 litres per metre cubed. Okay, so I hope that makes sense. We've just flipped that the way around, and therefore we invert the units. This is going to be okay because we've got milligrams underneath and kilograms on top. So when we multiply this through, these milligrams are going to cancel and it's going to leave us with the kilograms on top. Here we've got the meters cubed underneath, which is what we want. So let's just plug those in just to show you how they all cancel out. So 20 milligrams per litre times 10 to the power 3 litres per metre cubed times 10 to the minus 6 kilograms per milligram. If we have a look here, milligrams cancel out, our litres cancel out, and we're left with kilograms per metre cubed. So this is going to work. We just need to go through and multiply our numbers. So let's just do here 10 cubes times 10 to the minus 6. If we apply our rules for multiplying powers, that's going to be 3 plus minus 6, which is the same as 3 minus 6. So that's 10 to the minus 3. So we've got 20 times 10 to the minus 3 kilograms per meter cubed. And then we can convert this to scientific notation. So that's going to be 2.0 times 10 to the minus 2 kilograms per meter cubed. Okay, so 20 divided by 1,000 is the same as 2 divided by 100. That's another way of thinking about that. All right, so scientific notation or standard form. This would also be acceptable as an answer, but here we're just being complete because sometimes it's nice to be complete. Okay, finally, I want to have a look at question 5 because this one covers a lot of the concepts that we see in the present, also in question 4, and this is the kind of the extra one I give you. So here I give you an equation for this this constant. Let's not worry too much about what it is. So this is big G equals 3g little g over 4 rho curly p pi r. Okay, and then I tell you some things about the units of some of these terms. So little g is in meters per second squared. We use our square brackets to indicate the units. R is in meters, and rho curly p, which is Greek R, is density, and that's kilograms per meter cubed. Okay, so the first thing I ask you is to go through and think about what the dimensions of G are. So we can go from the units and think about what the dimensions of each of these units are. So remember, dimensions are L for length, T for time, and M for mass. And that's all we're dealing with here. We've got mass, we've got a length, or at least something derived from a length, and then we've got time, or something derived from a time. So let's just think about the dimensions. So dimensions of G, sorry, I'm going to write that down here. So that's 3. 3 doesn't have any dimensions. So meters per second squared. Meters is length. And then we have per time squared. And we're dividing that by 4. 4 doesn't have any dimensions. It's dimensionless. Then we've got mass per length cubed. Okay, volume is per volume here, per length cubed. And then pi, which doesn't have any dimensions, extend that over. And then we've got r, which is in meters, which is length. Apologies. Okay, so we can have a look at this. These that matter, these are dimensionless, so they're not going to contribute to anything in our dimensions. We've got an L down here and an L up here. So those will cancel. Those are the easiest ones to cancel. And then we're left with, on the top, t to the minus 2, and then down here, m and L to the minus 3. So we have dimensions of time, but per time squared, dimensions of mass, and dimensions of per length cubed. Now it's probably neater if we write these negatives. We can get rid of them by putting them on moving this one up here to make that L cubed, and moving this one down here to make it t squared. So exactly equivalent way of writing that would be length cubed for m t squared. Okay, so the dimensions of G, and we can write that again in another way, will be L cubed per mass per time squared. So we're left with dimensions of length cubed per mass per time squared. Okay, we've got, now I ask you about the units. So if we just take it, let's write down our dimensions of G again. Dimensions of G are mass, length cubed mass per time squared. Length cubed per mass per time squared. That's what we were left with. So we can also say, so what are the units of G? Well, we can just insert the values that we have, the units that we have for length. So the units that we have for length are meters, so they become meters cubed. The units we have for mass are kilograms, so that's per kilogram. And then the units we have for time are seconds, so that becomes seconds to the minus 2. So the units that we have of G, we can just go straight from the dimensions. So that's meters cubed per kilogram per time squared. Now you could go around and do this question the other way around and just calculate the units of G by going through and manipulating the equation, and you should come out with the same answer. On the answer sheets for the worksheet, I will tell you another additional thing we can do with this. I'm not going to go through it now. It's just an additional complication, but we can think about how newtons, the units of force, can come into this as well. But it's just really just ways of manipulating units, and that's all I want you to be comfortable with. All right, good luck.